sklearn Gaussian process regressor. Description: the Gaussian process regressor in scikit-learn is a powerful tool for regression tasks, particularly when you need to model complex relationships, capture uncertainties, and perform predictions with confidence intervals. It leverages the concept of Gaussian processes, which are probabilistic models that provide a smooth, continuous function that can capture the underlying trends and patterns within your data. Inputs. X. This is your training data, consisting of a 2D array where each row represents a data point, and each column represents a feature. Y. This is your target variable, a 1D array containing the corresponding values for each data point in X. Outputs. YPRED. This is the predicted value for the target variable based on the fitted Gaussian process model. It's a 1D array representing the predicted output for each input in the test data. YSTD. This is the standard deviation of the predictive distribution at each point in your test data. It provides a measure of uncertainty associated with your predictions. Steps. Data preprocessing. Your data needs to be prepared for Gaussian process regression. This involves scaling your features and potentially handling missing values. Kernel selection. You need to choose a kernel function that defines the covariance between data points. The choice of kernel determines the shape and smoothness of your predicted function. Common kernels include the RBF radial basis function kernel, Matern kernel, and polynomial kernel. Hyperparameter optimization. The kernel often has hyperparameters, e.g., length scale, sigma, that control its behavior. You'll need to optimize these parameters to find the best fit for your data. This can be done through methods like maximum likelihood estimation or cross-validation. Model training. With the kernel and hyperparameters selected, you train the Gaussian process regressor on your training data. Prediction. Once trained, you can use the model to predict values for new input data. The model returns not only the predicted values but also an estimate of the uncertainty in pay. Prediction metrics. Mean squared error MSE. This measures the average squared difference between the predicted and actual values. Root mean squared error RMSE. The square root of MSE, representing the average difference in the same units as your target variable. R-squared R-score. This indicates the proportion of the variance in the target variable that is explained by your model. Visualization plots. Prediction plot. This visualizes your predictions along with the confidence intervals. It shows how well your model fits the data and how uncertain your predictions are. Kernel function plot. This illustrates the kernel function you chose, showcasing its influence on the smoothness and shape of your predictions. Fine-tune parameters. Kernel. This determines the type of covariance function used to model the relationship between data points. You can explore different kernels to find the best fit for your data. Alpha. This parameter controls the noise level in your model. Higher values of alpha indicate more noise. N. Restarts optimizer. This parameter influences the optimization process for hyperparameters. It controls the number of times the optimizer restarts from random initial values. Random state. This sets the seed for the random number generator, ensuring reproducibility. Uncertainty methods. Confidence intervals. These provide a range around your predictions, indicating the degree of uncertainty. Standard deviation. This represents the spread of the predictive distribution at each data point, giving a numerical measure of the uncertainty. Challenges and fixes. Challenge 1. Overfitting. If the model learns the training data too well, it might not generalize well to unseen data. Sample use case that resulted in challenge 1. A model with a complex kernel and too many hyperparameters might overfit the training data. Fixes to challenge 1. Simplify the kernel. Consider using a simpler kernel like a linear or RBF kernel, which might prevent overfitting. Regularization. Use the alpha parameter to introduce regularization, which helps prevent overfitting by penalizing model complexity. Cross-validation. Use cross-validation to assess the model's performance on unseen data and identify overfitting early on. Challenge 2. Poor kernel selection. Choosing the wrong kernel can result in poor predictions in a model that doesn't capture the true relationship between your features and target variable. Sample use case that resulted in challenge 2. Using a linear kernel for a highly nonlinear relationship might lead to inaccurate predictions. Fixes to challenge 2. Experiment with kernels. Try different kernels like RBF, Matern, or polynomial kernels to see which best fits your data. Visualize kernel function. Plot the kernel function to understand its influence on the predictions and identify if it's appropriate for your data. Challenge 3. High computational cost. Gaussian process models can be computationally expensive, especially for large datasets. Sample use case that resulted in challenge 3. Training a Gaussian process model with a complex kernel on a large dataset can take significant time. Fixes to challenge 3. Sparse Gaussian processes. Explore sparse Gaussian processes, which approximate the full model and can be more efficient for large datasets. Subsampling. If you have a very large dataset, consider subsampling the data to reduce the computational burden. Approximate inference methods like variational inference can be used to approximate the solution, reducing computational cost.